Whether you are a cuber or not, watching a Rubik's Cube solve itself is a satisfying experience. This is not exactly a 2x2 cube, nor is it a cube for that matter. It moves like a 2x2 but has static centers like a 3x3, so it's impossible to roll without first spreading the corner pieces apart. And that makes it, in my opinion, a cool looking gadget. I don't believe it's ever been a real toy, but I saw it as an interesting challenge to make it all procedurally using geometry nodes in Blender. No need to brag and say it was easy. I hit some walls along the way myself, but I found the experience worth it and full of new things to learn. I hope you do too. Start with a cube primitive, followed by a split edges node. We have generated 6 separated polygons. To form the circles in the middle of each face, we have to create more geometry, so we will first subdivide the cube once and then extrude each side inwards. Add an extrude node. Leave the offset value to 0 and disable the individual toggle. At the moment we have overlapping geometry. To preview what we're aiming for, let's add a scale elements node and choose only the top faces as the selection. Now scale those polygons and see the middle section there. It has 8 points, the right amount for a minimal circle. The problem with the scale elements is that it only works on polygons or edges, but we need to tweak the points to shape them into a circle. Get rid of it and use a set position node instead. Again, connect the top part of the extruded geometry as the selection. Same as before, we will scale those points towards the center of the polygon. We have the position vectors of the points themselves, but not the center of the polygon. To get that information, insert a capture attribute node after the initial cube. Change the type to vector and the domain to faces. Now feed a position node to the attribute input. In this case, the node returns the average position values for all the points of a face. Now, because our faces are rectangles, those averaged vectors represent the center of the polygon. We inserted the node here to get the center vector info before the subdivision takes place. We will later make use of several capture attribute nodes, and to be able to tell them apart, I'm making it a habit to frame them and rename the frame. Call this one face center. Let's now calculate the right position for the points to shape a circle in the middle of each face. Subtract the face center vector from the actual position of the points and normalize the result. This returns a vector with the same length of 1 for each point. To customize this length, use a scale vector node. Our cube has a length of 1, so the radius of our circles should be shorter than half of that. Let's say 0.25. Connect the result to the set position node. What did just happen? What is this shape? Don't get alarmed. Our calculations are not wrong, not by much at least. Change the 3D view mode to wireframes and see that the circles are there, only at the center of the world instead of the center of the polygons. Think about it, we subtracted the face center vectors from the actual point position vectors. That returns vectors, meaning directions in space, but no actual position. Hence, the circles are placed at the center of the world. To place them where they belong, we need to add the face center vectors to the result and use the sum vector as the set position input. Switch back the 3D view to solid mode. We now have shaped the most basic type of circles in the middle of each cube side. Apply a subdivision surface to smooth the result. two problems arise. First, the corners of the cube are not connected. Remember that we split the edges before? That's easily fixable with a merge by distance node. The second problem is that the circles at the center have lost their shape as a result of the smoothing. Let's delete the inner circles before the subdivision and choose the top part from the extrude geometry as the selection. Now we have perfect circle holes, but the cube doesn't resemble a sphere at all. No problem, we can easily build a spherize modifier. Add another set position node, connect the position to the input, and normalize the result. After that, add a scale vector math node. We have formed a perfect sphere with perfect circle holes at each side. And because we are building this procedurally, we can control the radii of them all. Play around with the radii of the inner circles and the sphere also. Now it's a good time to color each side. I've already created two materials for this cube called faces and thickness. Insert a set material node after the cube and choose faces from the drop-down menu. This time we'll make use of a store attribute node to send geometry attributes to the shader tree. You can create output attributes using the standard way, but let's avoid long connection lines in an already crowded node tree. Change the attribute type to color and the attribute domain to face. Name it something meaningful like color. Because we are storing the attribute right after the cube creation, the values generated here will propagate down the node tree, and all the geometry that will be generated from this cube will inherit those attribute values. We will use the position vector for each face to determine its color. Switch the 3D view to material preview mode. We see nothing yet because we have not set the attribute for use in the shader editor. Hover the mouse over the Geometry Nodes editor and type Shift plus F3 to toggle between the different node editors in Blender. In the shader editor, make sure you're working with the right material and connect an attribute node to the base color socket. Leave the type to Geometry and enter the name we chose, in this case, Color. You should see the sphere in colors now. Red for X, green for Y, and blue for Z. Those are just the positive vector values. That's because color values are clipped into a 0 to 1 range. The negative spectrum is simply shown as black. Do not worry, we'll fix that in a moment. Let's separate the position vector field and work with each component separately. For the X direction, connect a greater than node and a mix color node soon after. If the X value of the position vector is positive, the face will be white. Otherwise, it will be yellow. Let's test the result and feed the value to the store named attribute input. The face of the positive x-axis is white and the rest is yellow. But let's be more precise. There's also the possibility that a face is positioned right in the center of the x-axis. Add an equal compare node, chained together with another mix node. If the x value of the position vector is equal to 0, the color will be black. Otherwise, it will be either one of the colors we calculated earlier. Feed this new result to the store named attribute input value. Now you can see the positive x side as white, the negative as yellow, and everything else as black. We're done with this axis. 2 more to go. But we'll be cutting corners this time. Duplicate the nodes holding Shift D and make the following changes. The axis to check against will be Y this time, and the colors will be blue for the negative side and green for the positive. Leave black as it is. There's a reason for that, and it will be apparent soon. Repeat the steps once more. This time the axis will be Z. If the polygon is facing down, it will be colored orange, and if it's facing up, it will be red. We have determined 3 different alternatives, one for each axis, but there's only one value input for our attribute. We will add the results together using either add vector math nodes or mix RGB, both work in this case, and connect the sum to the attribute value socket. Because we chose black in case the position value is equal to 0, if added with another color, the latter will override the black. See it for yourself. The next step should be thickening the shell. But because these are moving parts, it would make sense to separate them first. Time to use a split edges node. By default, it splits all edges, making every polygon a loose island. We don't want that, of course. We only need to split the edges that overlap with the X, Y, or Z axis, so their position along those axes is 0. Remember that an edge position is the average vector of both points that define that edge. Connect a position node to the selection input and separate its channels. Let's do the X-axis first. We'll check if the positions of the edges are equal to 0. Duplicate the compare node twice and do the same for the Y and Z axis. The split should only happen if the positions are equal to 0 on the X, or append an OR Boolean math node, equal to 0 on the Y, or even equal to 0 on the Z-axis. Replace the selection input with this new result. Now we have 8 separate parts that will rotate later on. In theory at least, because even if they are separated, their edges are still overlapping and nothing seems to change visually. How do we know for sure? We can move them apart to prove it, but for the animation to work we will have to move them apart anyway, so let's do it now. To calculate the direction of the parts, let's take a look at the original cube. Each point represents a direction vector from the origin of the object. It is along those vectors that will move the parts. How do we do that? By transferring those point position attributes from this original state and capturing those attributes onto the polygons after the first subdivision has taken place. That way each polygon will have a direction vector attribute embedded, along which we can move it later down the node tree. Insert a transfer attribute node before the first split takes place. The attribute type will be vector, the mapping method will be nearest, and the domain points. The attribute to transfer is position. Where do we want this vector field to be transferred? Insert a capture attribute node right after the first subdivision takes place. The attribute will be vector and the domain faces. Frame the node and rename it. Now connect the output field from the transfer attribute node to the input value field of the capture node. What did we just do? We have assigned a vector attribute to all the polygons that make up this cube. Each face is assigned the vector of the nearest point from the original cube. So all the faces that make up a corner have the same vector assigned. And because we captured this field at this particular state of the node tree, it is propagated down all the deriving polygons and consequently all the deriving points. Add a reroute node and let's return to where we left earlier after we split the moving parts. Append a set position node. Feed the reroute node from the capture attribute to the offset input. Now you can clearly see the corners split apart. To be able to control the offset precisely, let's modify the vector field beforehand. Insert a normalized node. This will scale all offset values to 1. And soon after, use a scale node to customize the length at your pleasure. Play around with the scale value. Right now we've got only a thin shell. How about we add some thickness? Insert an extrude node after the split. Disable the individual option and set the offset value to 0. Use another set position node, set the top part of the geometry as the selection, and connect a position node to the offset input. Make sure you normalize it first and then scale the resulting vector. This lets you customize the thickness, but now you must have noticed that the inner part of the geometry remains open. To close it, let's join the original part of the geometry, but first make sure that you flip the polygon normal direction so they face inwards. Wouldn't you like to have a different material for the thickness polygons? Easy. Insert a set material and choose thickness from the drop-down menu. This overrides our existing material, so let's use every polygon that is not part of the top geometry as a selection mask. There you have it. I like to use the bevel modifier to add some details around the edges. Geometry nodes is a modifier itself, so it can be stacked together with the rest of the modifiers. Set the bevel amount to 0.02 and increase the segments to 3. Expand the shading section and enter 0 as the material index. This makes it so that the beveled polygons get the thickness material. You can leave it here, but you will notice that only the outer edges get beveled. That's because although we joined both sides of the shell to create the thickness, we didn't in fact merge them. Be careful though, if we merge the points by distance at this stage, we reconnect all the edges that we split earlier and mess everything up. So disconnect the merge by distance node and insert it after the offset from the center has taken place. In the end, we'll move the corners back together, but more on that later. Let's move on. Earlier in the setup, we deleted the polygons that made up the inner circles, but our gadget will still need central parts. Instead of just removing them for good, let's put to good use the separate geometry node. Replace the delete node with it. Change the mode to face. Nothing seems to have changed down the node tree, but we now have access to the other part of the geometry as well, the circles. To have them match the contours of the sphere, we have to apply the same modifications to them as well. Duplicate both subdivision surface and set position nodes and feed them the circle geometry. Make sure to also replicate the thickness operations. Flip and join the back face, merge by distance, and the thickness material too. Don't bother recreating them by hand, duplicate them from our main branch. In the end, join both geometries together. As you can see, they match perfectly. In the example video, you can see concentric circles as the static part. You can do that too, following one of my previous tutorials. This brings the modeling part to an end. Next comes animation. Brace yourselves, more interesting things are coming. The rounded corners are the ones that move, so let's focus on them. The animation happens in 3 steps. The corner pieces expand, rotate, and then move back into place. We'll build a simple setup first and worry about automation later. Before we move on, let's disable the bevel modifier during the animation test phase. Insert a set position after the merge by distance node. We will rotate the position vectors of the geometry, so link a position node to the position input. Insert a vector rotate. Set the rotation axis to X for the moment and play around with the angle slider. The whole geometry rotates, but to imitate the movement of a Rubik's Cube, we need to filter out half of the corners. Let's say we want the right side to rotate. Separate the position field into its vector components and add a greater than node to the X output. The filtering is happening after the pieces have moved apart, so it's easy to filter out just the points whose X coordinate is greater than 0. Leave the angle at 90 degrees. Now the rotation part is taken care of. Let's set up the expansion movement. Without expanding, the pieces would intersect with the circles in the center, and that is not what we want. Add another set position node. Earlier, when we split the corners apart, we used the initial cube points as a moving direction. Let's use them again here. Normalize the scaled up vector and use scale again to customize its length. Moving the scale value up and down should drag the pieces away and towards the center. Switch the 3D window to the right orthogonal view, and you can clearly see for yourself that is not what happens. The corners move alright, but not all in the same way. The problem is that while we rotated the rounded corner pieces, the original cube points that serve as the direction for their expansion movement are still in place. So after the rotation, the corners move towards their original direction. To get rid of this problem, we'll rotate these direction vectors together with the geometry. The way I did it may seem a little awkward, but trust me, it works. Go way back on the node tree, after the original cube, add a mesh to points node. This generates a point cloud, which we will join with our rounded corners geometry. Switch the 3D window to solid view. You can see that apart from our rounded cube, the geometry includes the original cube points that hold the movement direction. We joined them before the rotation, so they are rotated together with the rest of the geometry. We can extract these transformed vectors easily using a separate components node right after the rotation. The geometry component we are interested in is point clouds, and same as earlier, we'll use the transfer attribute node to extract the position vector field from them. Set the attribute type to vector, select nearest points as the transfer mode, and link a position node to the attribute input. This returns the transformed point vectors, which, as you might have guessed, will be normalized and scaled before connecting the result to the offset input of the set position node. That is the core setup. Let me recapitulate what we have done here. We embedded the original corner points into our geometry so that they are transformed together, and later we extracted the transformed position vectors to use as the movement direction for our rounded corners. Whatever rotation amount we apply to the corner pieces, they will always expand correctly from the center. Now let's automate this setup in order to be able to repeat the transformation several times with options to change the axis of rotation. Select these nodes and group them. We will assume that all animation steps will happen in equal time intervals. Let's set up this interval. Link the frame information from the scene time node to the rotation angle input. Divide it by the length of the interval. I will have the interval 25 frames long for the moment. With each second that passes, the angle increases by 1 radian. Let's map this time interval to a 90-degree angle. Insert a map range node, leave the clamp option checked, and increase the output range from 0 to pi divided by 2. Hit play. Now the geometry rotates 90 degrees during the first second. Tab out of the node group and rename it to Animation. We want to be able to duplicate this node group and each instance to represent a new move for the cube. Right now, the cube rotates 90 degrees each second that passes, but we want to have more control. We want each node to store its move count and the rotation to happen based on that count number. Tab again inside the Animation node group, open the Group Properties doc and create a new group output called Move Count. Set the type to integer and the minimum value to 0. Leave the maximum at its default because we want to have a wide range of moves. Create a group input also called Move Count and add 1 to it. This way, each time a new group is added after the current one, this value will be incremented by 1. Tab outside and connect each move count output to the next input. Every node has its own move count, but we're not doing much with it. Tab in again. Instead of being driven purely by the time interval, we will control the rotation of the cube faces with a move count number also. Duplicate the move count group input, add 0 to it, and link it to the minimum input of the range map node. Add 1 to the move count and feed the result to the maximum input. Now the face rotates only when the time interval is equal to the move count. Nothing seems to change, but watch carefully now. Here comes the interesting part. Instead of rotating during the full time interval between move counts, we can limit this interval to only a segment of it. We can delay the rotation and also quicken its completion. This way there's a certain pause after each move. Set the minimum value to 0.25 and the maximum to 0.75. You can see the cube pause before each consecutive move. What comes next is the direction of rotation. Is it going to be clockwise or counterclockwise? Link a switch node to the maximum output range of the map node. Enter negative pi divided by 2 if false and pi divided by 2 if true. The switch itself will be controlled by a group input called counterclockwise. Let's test this. Tab outside the node group and have the second and fourth movements be counterclockwise rotations. Hit play and see the results. The next order of business is the axis of rotation. We want to be able to control it independently for each move too. Connect a combine XYZ node to the axis input of the vector rotate. Link an equal node to each of the components, and in the end, create a new group input and call it XYZ axis. Set its type to integer if it's not, the minimum value to 0 and the maximum to 2. Link this node to input A of all three equal nodes. Now we're able to control the axis of rotation by selecting 0 for X, 1 for Y, and 2 for the Z. Try it by selecting a different axis for each animation node. Hit play to check things out. Don't worry if things look messy. Important thing is that the axis is different for each move. There's still one thing to worry about: which side of the cube will rotate, the positive or negative side of the selected axis. This is going to be a short one. If you multiply the position vectors with the selected axis, the result should be a vector with only one coordinate whose value is not 0. Now it's a matter of checking whether that value is greater or less than 0. Branch the result out to a less than and a greater than node. The value to check against is 0. Feed both outputs into a switch node and control the switch status with another group input. Call it simply plus negative. Tab out of the node group. Now you can perform any kind of movement with this 2x2 type of gadget. Create some test movement sequences. Let's try the x-axis first. Clockwise, positive side. Then x-axis again, this time counterclockwise and on the negative side. Let's pause for a moment here and introduce you another great feature of the current setup. Because we made it dependent on the move count, not just time dependent, we can modify this move count to create pauses between moves. Let's see this in action. Make some space between the second and the third node groups and add one to the move count output before connecting the result to the move count input of the next node group. Now let's continue with the choreography of the movements. This time select the y-axis, positive side, clockwise, and last select the y-axis, negative side, counterclockwise. Test the result. Hit play. You can see that the cube pauses for one time interval before continuing with the third and fourth movements. We only added 4 movements, but you can experiment with as many as you want. The last issue is the expansion and contraction movements. With the current setup, it is necessary so the moving parts do not intersect with the static centers. The core is already in place. Now let's just automate the animation. We'll follow the same principle as we did with the rotation. Duplicate the nodes we added earlier to animate the rotation. To easily set the time interval, connect a new value node as the divider for the frame number. Shorten the interval to 15 frames. The expansion will happen during the first part of the interval, let's say from the beginning till about a quarter of its length. You can play with the expansion amount at your own will. I will go for 0.25 Blender units. As for the contraction movement, it will happen during the last segment of the time interval. Duplicate the last nodes again. Added the interval range from 0.75 to 1. Use an inverted value for the contraction amount, negative 0.25. Both expansion and contraction movements will be controlled from outside the group, so first add the initial movement result to the true input of a switch node, leave the false value to 0 and create a group input to control the switch. Call this input expand. Do the same for the second movement, only this time create a new group input called contract. We will combine the influence of these movements by adding them together and feeding the result to the scale amount. On each move, you can choose to enable or disable the expansion and contraction. Both movements will cancel each other out, but you don't have to do it for every move. Instead, you can do it for a group of moves. For example, you could enable expansion for the first move, do several rotations, and then contract the pieces back into place. This is what I have done with my example scene. I'll demonstrate it to you in a bit. But before that, let's reset the initial expansion value we already applied before merging by distance. It's simple. We'll repeat the procedure used to animate the movement. After the last animation node group, add a set position node, branch out a separate components node, add a transfer attribute to the point cloud output, choose vector as the attribute to transfer, select the nearest point method, and feed a position node to the attribute input. Next, normalize the vector output and scale the result. The value for the scale amount is the negative value we used to expand the pieces earlier, negative 0.1. This will zero out the initial movement, and now the pieces are back together, forming a sphere together with the central pieces. These are all the steps necessary to build procedurally and animate this gadget using geometry nodes. For the example scene, I referenced an already solved 2x2 cube on my iPhone. I discovered that if you repeat the following sequence of movements 3 times, the cube returns to its starting state. The sequence is as follows: left clockwise, right clockwise, top clockwise, bottom clockwise. This is the final scene where you can see that I've already chained those movements together. To add pauses every 4 moves, I've added 1 to the move count, so no property updates during that interval. As I said, I've repeated the sequence 3 times, and in the end, the pieces return to their initial state. Together with the static central pieces, this makes for a really cool looking effect. Remember, we can still modify the radii of the central pieces and the setup will still work fine. This subject took way longer to explain than I expected, but it is a complex one, and I hope I did a good job and taught you some new things about geometry nodes in Blender and proceduralism in general. Feel free to ask questions in the comment section, and if you like the video, please share the knowledge.